Hello to everybody, and welcome back to the AutoChem second annual workshop. I'm Aurora Ponzi from Ruđer Bošković Institute, Zagreb, and it's my pleasure today to chair this session in which we'll have three speakers. The title of the session is Theory of Attosecond Electronic Dynamics in Molecules. Before we start, let me remind you that you can write any comments and questions on the live Q&A box, and that at the end of the session, you will have the possibility to discuss with all the speakers in the breakout rooms. So it's my pleasure to present the first speaker of today, Alicia Palacios from Universidad Autónoma de Madrid. She's going to speak about time-resolved images of electron dynamics in atoms and molecules using the new capabilities of FEL and XFEL sources. So please, Alicia, as you know, you have 25 minutes, and then we will have time for some questions. Please, you can share your screen.
Okay, thank you. And thank you all for attending this session. So as Aurora introduced, I will be presenting today our recent theoretical studies on time-resolved images of electron dynamics in atoms and molecules using free electron laser sources. As all of you know, free electron laser facilities are proliferating all over the world nowadays, and the large investments are pushed by the many different applications of these sources. Probably the most successful ones nowadays are those related to the extraction of molecular structure in nanomaterials or in biomolecules. However, the characteristics of these sources, and in particular the high brilliance, the high intensities, and the tunability over a wide range of frequencies, make them also ideal in order to explore problems of interest in atomic and molecular physics. And this is what I will be talking today on gas phase experiments in atoms and molecules with these sources. And to do so, we also have at our disposal nowadays a large pool of spectroscopic techniques that are able to measure light with different types of photodetectors, or also measure charged particles with a very high energy resolution. It is also possible with specific devices even measure the direction of ejection of electrons and photoions, and sometimes even all in coincidence. So with all these tools, we are ready now to explore new nonlinear phenomena arising in atoms and molecules that have remained unexplored experimentally until now. And this is what I will be talking. In particular, I will focus first in small targets, helium and hydrogen molecule, because in these targets, we can perform nearly exact calculations in order to get real insights on the fundamental mechanisms that are induced by these sources. Then one can transfer all this knowledge into more complex targets, such as small biomolecules, where one can pursue more ambitious goals, as making reality, for instance, attochemistry, that is to say, manipulating the chemical properties at the attosecond time scale. So in spite of the apparent simplicity of helium atom, the number of experimental and theoretical works is always increasing. We have here some very recent works. And the reason behind is mostly the fact that with this target, one can learn a great deal about electron correlation and the role of these terms in many nonlinear phenomena that were inaccessible until very recently. And with the free electron lasers, now we can explore them. And the most basic nonlinear process is, of course, the two-photon absorptions. What I'm showing here is some recent theoretical data on two-photon single ionization of helium. On the left, we have the energetics of the atom. And here I'm showing the apparent cross-sections as a function of photon energy. When two photons are absorbed, one can reach two different final symmetries, S and D. The black line corresponds to the total cross-sections. At these low photon energies, we have just two photon absorption below threshold, and after 24.6, what we have is two photon single ionization, where the first photon already lies into the continuum. And if one aims to get more detailed information beyond the total probabilities or cross-section, one can also extract the photoelectron angular distributions here are plotted for specific photon energies. As you can see, both the dependencies with energy present very sharp structures, and also the angular shapes are strongly changing with the photon energy. And basically what these changes are telling us, are capturing, are the very different mechanisms that are happening and are dominant at the specific photon energies. And I will go over some of them in the following, but first let me briefly comment how this data has been obtained. We solved the time-dependent Schrödinger equation in full dimensionality. So in the first step, we just perform a time propagation during the presence of the pulse. We use a numerical representation of the wave function using a finite element method within a discrete variable representation. Once we have the propagated wave packet, one could directly project into the final scattering state, or alternatively, one can implicitly propagate to infinite times, which is indeed equivalent to solving the time-independent Schrödinger equation using as right-hand side the time-propagated wave packet. By solving this equation, one can get then the scattered wave from which we can extract the ionization amplitudes, which are just simply expressed as a surface integral. This methodology was developed several years ago, and now in the last work, we have extended it in order to include the possibility of extract angular distributions for the single ionization channel. So let me go back to the results, and let's focus first in this region where we have the sharper sections. And as you may recognize, these are the typical asymmetric profiles associated to a Photon profile. And what we are looking at this around 3B, where we are looking at the 2-photon single ionization reaching the optically forbidden doubly sided states that, of course, they are optically allowed by a 2-photon transition from the ground state. And these profiles are the result of the interference of the 2-photon direct background and the delay ionization process of the decay of this doubly sided state. And nowadays, with the free electron laser capabilities and the high energy resolution of current devices of magnetic bottles, it is possible to extract the angular distributions in a fine scanning energy over these Photon profiles. And what I'm showing here is how strongly it can vary the angular or the direction of emission of electron just in less of half an eV. If we focus, for instance, in this row, we are going around this Photon profile, and we can see that at some specific energies, for instance, the electron is leaving the atom completely losing memory of the direction of the light, which we use to irradiate the atom. And this is basically due to the fact that the doubly sided states somehow live enough, both electrons live long enough excited before they decay into the continuum that they forget memory, they lose memory of what was the initial direction of the light. So with this, we can learn a great deal, and indeed with these distributions, what we are obtaining is a direct image of the electron correlation terms that are important in these final states. If we now move at the slider photon energies, we see these enhancements in the cross sections, and these are related to the so-called core-excited resonances. These resonances were already described in previous works in the context of infinitely long pulses. The longer the pulse, we will see that these enhancements are more pronounced, and we find an enhancement associated to the excitation of the helium plus. So what we are seeing in this process is a 2-photon single ionization, where the first photon ionizes helium, ejecting the electron, and the second photon, which is in resonance with a transition between the ground state of helium plus and one of the excited states, actually what it's doing is exciting the ion. And of course, we are going to find different enhancements as we have different excitations lines. And the interesting part, if we look at the angular distributions, is that they perfectly capture this strongly uncorrelated behavior in the electron emission, and we can see we have almost a cosine square shape, typical, or is the same basically that we found in the 1-photon single ionization process. If we now move even to higher energies, we see that the electron angular distributions are slightly changing. And even though in these cross-sections we see a very small behavior, if we take a specific energy and we look at the Photoelectron Spectra, we can get a greater deal of information. And indeed, we are now in a collaboration with Carlo Calegari and Kevin Prince at Fermi, where future experiments will be performed in this region. So let me show you the Photoelectron Spectra at a specific energy, in this case 61.67. This is illustrated here on the left. At this energy, we are in resonance with the one photon absorption now with this doubly excited state. So we are exploring now the symmetries of p state, and we will look at the two photon single ionization photoelectron spectra. This is plotted here, in this case for longer pulses and higher laser intensities in order to compare properly with experimental data. So the blue lines here correspond to the ionization, leaving the helium plus in the ground state. So this is the one photon absorption, the two photon absorption, 3, and so on and so on. This colored series correspond to the two photon single ionization, but leaving helium plus in excited states. Okay, and we can see also, of course, the series for the 3 photon living in the excited states and so on. And the interesting part is that now we can change the laser parameters with in a quite accurate way in free electron lasers. What I'm showing here now is different results for the slightly different central frequencies of the pulse. And of course, we see that these peaks are slightly shifted depending on the energy. And more importantly, we see that the relative ratio between these yields is actually changing. And this is happening more strongly here, this energy which is exactly in resonance with the first excited state of p-symmetry. So what information that is being encoded here are the different electron correlation terms that are defining these doubly excited states. This is work in progress, so further analysis will be done. And what I'm showing also here in this yellow line that I didn't commented before are actually the two photon double ionization yields. And this is an important piece of information when looking at these high intensities, which is the fact that one needs also to quantify not only the single ionization process, but also the double ionization process, because as you can see, they lie in the same lines and in the same positions at the single ionization, and they may significantly modify the yields. So this is to take into account, because indeed single and double ionization are competing in a long range of frequencies. In particular, after 39.5 eVs, the double ionization is also open, and both single and double are proceeding simultaneously. However, if we use one of these devices with electrons and photoions are simultaneously detected, then one could unravel these different processes. And let me show you what it could be extracted if one analyzes now the double ionization process, because also quite a lot of information is encoded there. These are all results that has been only performed theoretically, but now with the current capabilities of free electron lasers, it will be possible to access and extract this information. And just briefly, what we have here is the electron distribution of the second electron with respect to the emission direction of the first one in the double ionization process. And what we observe is when we are using energies in which the two photon double ionization is happening in a sequential way, that means both photons must to be absorbed in order to eject electrons. We see a behavior, a quite correlated behavior. Both electrons are speaking to each other and they live in a back-to-back, so they have a strong repulsion. But when we are using and we are looking at the same process with higher photon energies, where the sequential process is possible, that means one can ionize helium and then the second photon can ionize the helium plus. So in a similar problem as we saw before with the core-excited resonances, then we go back to this quite uncorrelated behavior in the electron emission. More interestingly, with free electron lasers nowadays, we can even appeal and we can even look at the time scales of these processes, because if we just look at these sequential and non-sequential competing processes, and we just using and we irradiate the atom with shorter and shorter pulses, we see that this uncorrelated behavior goes to a quite correlated one. So basically, it's given us information at the time that takes this sequential process to happen. So all this data should be revisited now, that now we have the capability of really accessing experimentally. So in brief, free electron lasers, even in atoms, allows to understand how relevant electron correlation is for different mechanisms. Only analyzing photoelectron spectra, it is possible to characterize the correlation in doubly excited states and the time scale of these processes. This is relevant in autoionization, but also in the analog processing multi-electronic targets as the Auger-Meitner processes. And if one also count with electron photoion coincidences, it will be even possible to unravel competing processes and even extract the time scale of multi-photon ionization or excitation schemes. Now let's go to molecules, and let's look at the same process, photon absorption, nonlinear process in hydrogen molecule. And let me start again by revisiting some old data. So I'm going to be looking at the two-photon single ionization now in the molecule. We again solve the time-dependent Schrödinger equation, but in this case we use a spectral method. So basically we expand the wave function in a Born-Oppenheimer-Vibronic eigenstate, and still the laser molecule interaction is treated within the dipole approximation. In this old data, the one thing we observe is that if we look now again to the probabilities as a function of photon energy, as we did before, and we use a 2 femtosecond pulse, we have very small distributions. And in this particular case, we can also look after ionization if the molecule remains bounded in a non-dissociative state or if it's dissociated. What we observe for very short pulses is that the molecule doesn't have tiny enough to move. So basically, the non-dissociative ionization will dominate, which is what is observed also in a photon absorption process. However, when we use longer pulses, we observe the appearances of different structures. And not only that, if we go to the energies that are in resonance with the intermediate states, we even see that the dissociative ionization may overcome the non-dissociative. And this is due to the fact that during the duration of the pulse, the nuclear have time to move, and we are exploring different nuclear geometries, different internuclear distances, that when the second photon comes, is reaching the target into different final states, and one can even control these two different ionization channels. And just a few years ago, free electron lasers, in particular an experiment performed at Fermi, demonstrate that this was possible, and we could obtain this relative ratio between dissociative and non-dissociative in an experiment led by Daniele Dueck and Michael Meyer. And now we are working further in trying to explore, as we did in the case of atoms, the angular distributions, and trying to explore more information of this coupled electron-nuclear motion and how these time scales are reflected in the final observables. And this is work in progress, in which we are also pursuing to look at the same processes but using two XUV pulses. So as a summary, the two photon absorption in molecules is even richer because the interplay between electron and nuclear motion allow us to manipulate in time the different multi-photon paths, and we can even control these ratios. And of course, the next natural step will be to just use these phase control pulses in order to get further time resolved information. So now let me put what happened if one use slightly higher photon energies available on free electron lasers, and I will be focused in just the region of soft X-ray frequencies. But also we now exploit the possibility of using relatively high intensities of these lasers. And when one uses very high frequencies already, a new phenomena come into play. Let me just give you an example of a very recent experiment performed in the helium atom. In this case, was only synchrotron radiation, but at very high frequencies. And what they observe is the appearance of compton scattering. So one can with a very high frequency, and one observes also the emission of a less energetic photon that brings the atom, in this case, into excited or ionized state. And this was observed very recently in this experiment. Of course, instead of using just monochromatic light, one can, with two different frequencies in such a way that this process can be stimulated, one can increase the signal of this process. And this was shown in atomic targets also, in this case in theoretical work in the group of Henri Vachon, where they explored the possibility of looking at the stimulated compton scattering by using, whereas a single pulse with a broad bandwidth in such a way that the emitting, the photon stimulating the scattering is within the bandwidth, or using two different pulses with two different colors. And this is what we now have tried to implement in the case of the molecular case. So let me start first by the use of a single pulse, where we have a very high frequency within the pulse and a lower frequency still within the bandwidth that allows to go back to the ionizing or excited states of the molecule through this stimulated compton scattering. And in this case, we again solved the time-dependent Schrödinger equation, but since this was a proof of concept, we just kept ourselves within the fixed nuclear approximation. But in this case, what it strongly changes is the laser molecule interaction potential, since at these very high frequencies, the dependence of the vector potential with the spatial coordinates cannot be neglected any longer. So what we take is the vector potential, and we just perform a Taylor expansion and just kept the two first terms. That is to say that we are just including correlation terms to the corrections to the first order of 1 over the speed of light. As a consequence, the interaction potential now has this expression in which we have the same dipole term, and now we have a non-dipole correction. And this is actually necessary because, as expected, at these high energies, the dipole approximation is going to break, and we have to introduce these corrections. So the first thing we look is actually at a Raman process. So we look at the excitation into these states by using a very short pulse. We use a Gaussian shaped pulse and a relatively high intensity. And we look at what are the excitation probabilities for the full molecule as a function of photon energy. We can see that at very low photon energies, still the dipole approximation could do a good job, but very quickly the non-dipole terms take over, and they are necessary in order to properly represent this Raman scattering or these excitation probabilities. If we now look at the photoelectron spectra, this is what we obtain. These are the density of probability, ionization probability as a function of electron energy. What we find here is the typical one photon absorption peak. So this is the absorption by the first photon. We have also have the ATI peaks, the ionization peaks for the 2 photon absorption, 3 photon absorption, and so on. But what we are looking at very low electron energies is precisely the signature of the stimulated Compton scattering. And now let me blow up this region and do a more careful analysis. And what I'm plotting here is the initiation probabilities, in this case for 3 different molecular orientations with respect to the light. And since we are not in the dipole approximation any longer, we have to take into account not only the light polarization direction, but also the light propagation direction, which give us a new knob of control with respect to the molecular axis. So while in a dipole approximation, we will be talking about parallel or perpendicular orientation, here we have now 3 different configurations of that. So the blue line corresponds to the total yields, and then we are plotting here including the relative contribution of the dipole and non-dipole terms that, as you can see, vary strongly depending on the orientation of the light with respect to the molecule. The interesting part here is that now dipole and non-dipole terms are reaching the same final state, the same total energies. However, they are doing it reaching different final symmetries. As you may guess already, the consequence of that can be nicely captured if we look at the angular distributions, because the superposition of these different symmetries are going to make possible to see an asymmetric electron emission. So by controlling the relative orientation of the molecule with respect to the light, now one can control the electron emission in a specific direction. And just to be clear, if we were working only in the dipole approximation, we wouldn't see this asymmetry. Again, if only the non-dipole terms will be relevant here, we will also observe a quite symmetric emission with respect to the plane of the light. But since we have a superposition of both, we can have this electron emission. And as I said before, we can work with a very narrow in time pulse, so very broad energy bandwidth, but we also can play with 2 pulses and then make the Compton scattering just with specific frequencies. And in this case, we have an added knob of control, which is the relative angle between the 2 pulses. And as you can see, by varying the relative angle of these 2 pulses, one can actually drive the electron emission in specific directions. So when using high photon energies and high intensities, one have to come to a different framework, theoretical framework, incorporating, for instance, non-dipole corrections, but also we can address very interesting new phenomena as the case of stimulated Compton scattering. As I introduced in the first slide, all this knowledge now we are aiming to translate it into large molecules. As you could see in some of the posters of our group in these days, we have done the first 2 photon single ionization and 2 photon double ionization studies in very large molecule. This is an example on glycine. Of course, the first step, which is the single photon ionization step, can be still accurately represented using a full quantum mechanical treatment, as long as we keep within the fixed nuclear approximation. However, in these large molecules, if one wants to include the coupled electron-nuclear motion, we have to go to more approximated methods. And in particular, we have to treat now the nuclear motion with a classical approach. Still, we can get quite decent descriptions of the problem. We can even include the proof step and looking at the different fragmentation channels. And in particular, in this recent work, we could already follow the main trends in which specific fragmentation channels are carrying out information in the pumped target in different cationic states. So this is now possible. And now we have transferred part of this knowledge to go to pumping these kind of molecules, but again in the soft X-ray regime. And this is a work in progress in which we are studying now the aminophenol molecule in particular. We are using a pump pulse of 260 dB. It's still low enough that we don't reach the inner cells, but still what we observe is that by using these large pulses, we still create a wave packet of valence states, and we observe what has been described in many other works and many other groups of this process of ultrafast charge migration around the molecular bomb. And if we now look at how these charges in different sites of the molecule are varying with time, we have quite sharp oscillations. Of course, this is in the fixed nuclei. If we now want to take into account the initial distribution of the ground state, that by computing different equilibrium distances, so in this case we did it with a Wigner distribution, we see that these oscillations are partially damped, but still they will be visible and they have an amplitude that is equivalent to that one found and experimentally measured in amino acids. And the observables in this case can be different approaches, and this is work in progress in a collaboration with James Cryan and Ago Marinelli from SLAC. And in the case of these molecules, there are many other groups working also with soft X-ray, but in this case using it as a probe. These are just some examples in which the pumped molecule can be excited or ionized with UV or mid-infrared, and then the X-ray probe is the one that is used really to extract the time-resolved information. So as I hope I could convince you today, free electron races are actually giving access for the same time, for the first time, to many processes. For instance, one can access electron correlation in initial, intermediate, and final states. One can get the time scales of processes such as ionization or JDK or multiphoton ionization. And in the case of molecules, one can even exploit the interplay between electron and nuclear motions in order to control the outcome of a reaction. And as well, we saw if we play with very high frequencies, new nonlinear phenomena that are still to be experimentally proved are at hand. And let me just finish. I'm just presenting the people who actually have been working in all these different topics. The results of helium atom, they were mostly obtained by Diego Bol in a collaboration now running with Johannes Feist. And all the work I'm doing always in molecules is always in collaboration with Fernando Martín. I saw results for the hydrogen molecule from Roger Bello and in particular Arturo Sopena in a collaboration with Henri Vachon, who is the guy who brought us into the world of Compton scattering. And then I have shown the last snapshots of biomolecules with people also within the group of Fernando Martín and in a valuable collaboration always with Piero de Cleva. And thank you all for your attention. I hope I didn't close too much the time.
Okay, no, it's perfect, Alicia. Thank you for your nice and rich presentation. I don't see any questions at the moment, so I have a very quick question. If I correctly understood, you mentioned that stronger asymmetries are produced if the dominant contribution comes from the non-dipole effects. Is this can be considered as a general statement, or it is true only for this specific case, or I don't know, just if you can comment.
Yeah, okay. In this case, the thing is that now when we are using these high frequencies and we are looking at the low electrons where Compton scattering manifests, what we observe is that we have always these two contributions.
Okay.
The
dipole and non-dipole.
But also the non-dipole. And the fact is that since these two guys, because of the symmetry of the operators, are reaching different final states, you will always have a superposition of the same final state with different symmetries. So this is what leads to this asymmetry. So as long as you have both terms contributing, you are expected to observe an asymmetry. So let's say there's a large range of frequency and electron energies where this asymmetry can be manipulated. So
okay. I see. Thank you.
Sure, thank you.
I don't see any questions, so the audience can speak and discuss with Alicia later at the end of this session. So thanks again to Alicia, and we can go on with the second speaker of this session, who is Benjamin Lazorn from Université de Montpellier. He is going to speak about on the preservation of coherence in the electronic wave packet of a neutral and rigid polyatomic molecule. So please, Benjamin, the stage is yours. You, as you know, you have 25 minutes, and then we will have time for some questions. Please, you can share your screen.
Can you see my screen?
No, I cannot see your screen.
Okay, I'm really sorry, because in the preview options, I can show broadcast preview, backup stream 1, backup stream 2, or main stage.
Maybe.
Oh, sorry. Yeah, sure. Can you see it?
No. Maybe John can share. Okay, yes, now we can see your screen.
Okay,
Perfect.
and then previously. Oh, sorry. You can see my presentation?
Yes.
Good.
Yes, we can.
Okay.
Okay.
Sorry for the inconvenience. So, well, good morning or afternoon, everyone. I don't know, because it's noon. And well, first of all, I'd like to thank the organizing committee for inviting me to give this talk today, which is essentially the summary of a collaboration that I've been having with the group of Agnes Vibok in Debrecen, with also Gabor Alash, Andras Csehy, and Peter Badanko. So in collaboration with myself in Montpellier in France. So the context of this project is, well, actually an older project. It's based on an older project that we like to call the Ozone project, that started in 2012 in collaboration with Fabien Gattier at the time in Montpellier, myself, David Lauvergne in Orsay in France, and our PhD student Aurélie Pervot. Also involving some collaboration with Michael Robb in London for calculating quantum chemistry data, and from 2015 with the group of Piero De Cleva in Trieste in Italy for calculating improved time result photoelectron spectra. All of this was initiated by Agnes Vibok and Gabor Alash in Debrecen, with an objective shared with experimentalists in the group of Reinhard Kinberger in Garching in Germany, to monitor attosecond coherence, so an electronic wave packet, so to say, in a neutral molecule, conducting pump probe experiments and doing calculations and modeling of such situations. So the project has been financially supported by different bodies in Europe, in France and Hungary, and European bodies as well. So here you have the latest paper that we published all together, which is a theoretical and experimental paper, where we showed how to monitor and probe an electronic wave packet in a small molecule, namely ozone. So our objective is to essentially go from attophysics to attochemistry. And by this, I mean that we'd like to create a coherent superposition, an electronic wave packet or a molecular wave packet in a neutral molecule without ionization. Ionization can be used in a second stage as a probing measurement, but not as the pump. So that's our frame of mind, so to say. So what we want to do is to create such a superposition of several electronic states in a neutral molecule, And why would that be useful for chemistry? It's because we could then create some kind of specific initial condition that would direct chemical reactivity in a neutral molecule rather than in a cation. So there are some technicalities that have to be overcome on the technical front, on the experimental front, but also on the modeling front. So essentially, we are considering that a very short pump can have a large enough bandwidth so as to create such a superposition. This could be in the few femtosecond domain or in the sub-femtosecond domain because we are in the UV. So we are limited by technical constraints. Now, the essential questions that are to be asked in such a context are, should we consider that the nuclei will be moving enough to induce possible decoherence of the electronic system? Will non-adiabatic effects be essential in this context? And probably they will. And can we then consider that photoreactivity could be coherently controlled over long enough timescales? Or is it likely that this coherence will be destroyed very early on? And can we play with this coherence, or is it too sensitive? And such questions have been much addressed in the context of charge migration versus charge transfer in cations. Now, our objective is to see how they translate into the world of neutral molecules. So as I told you, we are facing technical constraints because if we want to excite neutral states in the molecule that are not too high in energy, say in the UV domain, so the first valence states of a molecule, say if we are around 4 electron volts, then we have to deal with pulses of typical durations of 1 femtosecond and make sure that within the envelope we have some cycles, and so we are really dealing with few cycle pulses here. But then we, as I told you, that's a collaborative project, and actually we used parameters that are relevant for experimental setups that could be actually carried out in the group of Reinhard Kinberger. Okay, so our first molecule of interest was ozone, for which we showed that it was possible to create a coherent superposition between the ground state and the first excited state, or one of them, B here, typically called B. And we showed that indeed we could monitor a revival of the coherence even if the pumping of the molecule induced some dissociation of ozone into O2 and O, then we could still see some of the wave packet going back and forth for a while before a full dissociation. So we could monitor this coherence, calculate it with computations, but also observe it with experiments. Then we decided to go further and consider other types of molecules that would create and that would avoid too much dispersion in the wave packet. So we looked for rigid molecules with valence excited state that could be coherently populated with a pulse that could be achieved experimentally. So we looked for a molecule for which we could have two states with similar oscillator strength within a bandwidth of about 1 to 1.5 eV, so as to consider pump pulses with characteristic times of about, well, a few femtoseconds, and states that would be located around, say, 6 eV, so typical UV for an organic molecule. And we found pyrazine as a good candidate because it exhibits around 6 EV2 states. Here you have the experimental spectrum. You've got the B2U singlet and the B1U singlet that are around 5 EV for one and 6.5 EV for the other. So be careful that there is a rescaling of the spectrum. So in fact, the two bands are have very similar intensities here. And pyrazine, by the way, is also very famous in quantum dynamics because it's one of the benchmarks for calculating electronic spectra, absorption spectra, in which you have non-adiabatic effects due to conical intersections. So, a lot of papers have been published on the B2U state here, the shape of which is very much altered by a vibronic coupling and non-adiabatic coupling with the lower state here, shown here, that shows some strong intensity borrowing. So with this at hand, we consider to address several questions that are relevant in this context. So, for instance, at early times, we know that a rigid molecule, a bound molecule, quite rigid, will show dynamics quite approximated by a quasi-harmonic description. And we know also that if there is symmetry, this symmetry will be essentially quasi-classically preserved. So the essential modes that will be activated first after absorption are the totally symmetric modes that do not lower the symmetry of the molecule, which means in that molecule 5 vibrations out of 24. And then IVR will start at some point, but then for short times, say 20 femtoseconds, we can consider that IVR will be moderate, and that non-adiabatic couplings will also be moderate because they will require some vibrations in the molecule to access places where there are conical intersections. So we decided to consider a model based only on the totally symmetric vibrations that allows us to prevent non-adiabatic coupling between states of different symmetries, and to consider that IVR will first take place within this reduced subspace, and then after the wave packet has time to breathe, it will populate non-totally symmetric modes. But we also consider that because we had this model available for us, we could also push it to longer times as a proof of concept to see how much coherence will be destroyed, how fast, how efficiently or not. And so in this context, we could probe the role of anharmonicity compared to a harmonic approximation, and also the effect of considering or not the dependence of the transition dipole with respect to nuclear coordinates. That's to say, whether a Frank-Condon approximation is enough, or if we should consider a Herzberg-Taylor description to account for this dependence on the nuclear coordinates. So here is a bit more about this 5-dimensional subspace of vibrations that preserve symmetry that I mentioned. So you have a representation of those vibrations and some calculations that we did to check that our level of theory was good enough compared to experiments or other levels of theory that could be considered as good enough as well. So then we were happy with our level of theory, and we produced a 5-dimensional model of potential energy surfaces. Now, okay, I told you we want to create a coherent superposition of two excited states. So we need to make sure that we can populate them according to selection rules. And in this case, because there is a lot of symmetry in that molecule, we have selection rules. And in fact, the two states that I considered before, B2U and B1U, they are polarized along here, the Z-axis and the Y-axis, which are the directions along which you have a non-zero transition dipole. Here, mu03 and mu02 for the two states 2 and 3 that are B2U and B1U. So for populating them coherently and with similar populations, we have to consider that the electric field is polarized along a direction that is in between those two active directions for photoactivation. So which is why we consider that green arrow here at an angle of 45 degrees between the two active directions. Now, a bit of chemistry on the states to understand what they are and how we can interpret them in terms of transitions between orbitals. So here you've got essentially a reduction of the wave function to what dominates the description of such states. It's very similar to benzene, in fact, but within a D2H group rather than a D6H group. And here, actually, the orbitals that matter for understanding the states are those four orbitals that are the pi and pi star degenerate frontier orbitals of the system. Well, they are not really degenerate in pyrazine. They would be degenerate in benzene. So considering different types of single excitations between this set of four electrons in four orbitals, we can understand quite nicely those two states that I mentioned, B1U and B2U, in the spectral domain around 5 to 6 eV. And then there is a second pair of B1U and B2U states that would be degenerate in benzene that are high enough in energy, around 7 to 8 eV. So they are quite isolated and everything is quite nice. In fact, it's quite simple. So then with this model, we perform different types of calculations of absorption spectra using the modules implemented in the Gaussian software, and also doing Fourier transform of wave packet propagations with MCTDH, which is a program for propagating a wave packet in time, and that can be used to reproduce an absorption spectrum from Fourier analysis. So here we considered four cases, four different types of approximations. H plus Fc means harmonic plus Franck-Hunden. H plus HT means harmonic plus Herzberg-Teller. And then A means anharmonic. So considering, so to say, Morse potentials rather than quadratic potentials for the potential energy surfaces that we considered. So here, what you can see is that essentially the S2 absorption spectrum is almost insensitive to the four different approximations or settings, while we see an effect of anharmonicity or Herzberg-Teller instead of Franck-Hunden on the S3 spectrum. Essentially, Herzberg-Teller description of the transition dipole as a function of the nuclear coordinates changes the intensity of the spectrum, but not so much the spectral position of the vibrational peaks within the electronic spectrum. On the other hand, you see that the anharmonic description compresses a bit the spectrum at high energies as expected, because the levels are not equidistant anymore. Other than that, the intensities are quite similar. So on the spectrum, we don't see much effect of being very crude in the approximation using harmonic and Franck-Hunden, or being a bit more flexible. Now, what about time? So here you've got a representation of the transfer of populations over time, and also in black the pump, the spectral envelope, well, not envelope, but the pump, the electric field as a function of time. And you see that we considered settings of the pump that are such that we could achieve equal transfer of population to S2 and to S3. So you see that the plateau here at 10% is about the same for both states. Here on the bottom line, you see the envelope, the spectral envelope of the pulse, and the absorption spectra of the two states, to show you again that we really populate those two states with such a pulse. Now, told you we are interested in coherence and electronic wave packets. So, well, the typical measure of coherence is written here in a reduced way, in a sort of renormalized way, C of t, and you see here that at short times from here, from 10 to 100 femtoseconds, we have a coherence that shows oscillation patterns, and such oscillation patterns are quite similar for all cases that I mentioned, all types of approximations. So such approximations are not so critical, in fact, at such times. Then again, I told you that we pushed the model to times that are not physical, because we know that here on the bottom line, over 1 picosecond, we know that other effects will act. So we will have IVR to non-totally symmetric modes and internal conversion via conical intersections to other states. But as a sort of mind game for proof of concept, we calculated the coherence at very long times to check whether we would still have recurrences, revival of coherence, and whether such approximations had much effect or not. So you see, somehow, well, the effect of approximations is not so high, but then yet some cases preserve better coherence than others. So to have a clearer interpretation, we thought, okay, well, coherence, that's a measure of, the possibility of an actual electronic wave packet. Can we relate this to other quantities that will evolve correlatively with the coherence? So, well, quite naturally, we decided to look at the autocorrelation function of the wave packet, which is a measure of how much it goes back and forth and reconstruct itself compared to what it was originally at 0 time. So you see that there are some oscillations in the yellow curve that are, well, not dissimilar to the coherence, but that's not very satisfying, because sometimes, yes, they oscillate in the same way here, for instance, but here it's difficult to say something clear. Then we thought, okay, well, another aspect that is probably very relevant for the destruction or preservation of coherence is the dispersion of the wave packet in space, which we call the compacity here, K, which is a sort of measure of how of the total width of the wave packet. And you see here that the magenta curve shows oscillations that kind of follow also the global envelope of the coherence, but not always. Then it's an interplay between probably width, but also more subtle phase effects that we are monitoring here. So here I'm showing you a comparison over time of the coherence with the for different types of approximations. So here you see harmonic and harmonic. On the bottom left corner, Hasberg-Teller, upper right corner, Frank Kunden, sorry, here. So you see essentially, well, the behavior is the same, and the conclusions are that a large coherence requires a small compacity, which is quite intuitive. We don't want the wave packet to spread too much so as to conserve coherence between the two electronic states. And this tendency is observed in all cases. Right, then we thought, okay, that'd be nice also to have a more detailed description of the electronic wave packet as a real electronic wave packet, as a motion of the electronic cloud. So for this, we considered reduced densities. And so because we are considering a coherence between different states, 3 here, the ground state and the two excited states, we have to consider transition densities, one electron transition reduced densities, and also total densities. But if you plot total densities, you won't see any difference. It's too subtle. So we focused on the differences between the density of the ground state here, rho 0, 0, with the excited states. So delta 02 and delta 03 are density differences. And for completeness here, you can see the density of the pi and pi 00. Now, combining such quantities and evolve with coefficients that are due to quantum dynamics, we could generate that film, that movie of the electronic density changing with time. So you see that there are quite complicated oscillation patterns that are dictated by coherence here. So the curves here are the coherences that have oscillation behaviors, while the populations are constant. So that motion is really due to the time evolution of different coherences between the three states. And you see here a nice motion of the electron. But that's not something that we could monitor easily with experiments. So we also considered the total permanent dipole, but time dependent now, because we are considering a molecule that is experiencing a superposition of different electronic states that change over time. So the total the permanent dipole, sorry, will also be a function of time. So here you have the trace of this dipole. So the full black arrow is the dipole at time 0, and the dashed one is the dipole at a longer time, and you see that it does a sort of nice pretzel-shaped oscillation over time. So that's something that maybe could be observed experimentally with an experiment that would probe the time evolution of a permanent dipole in a molecule. So now I told you we considered a limited model to limited to the totally symmetric vibrational modes, and we should go further. So obviously, well, I told you, well, being further experimentally would be to have a setting that shows the evolution of a dipole, or perhaps a quadruple, but some kind of property of the molecule. But in terms of calculations, we should account for longer time IVR with dispersion to non-totally symmetric modes, which means that we have to account for 24 modes instead of 5, the effect of non-adiabatic couplings, the possibility of transferring population to other states, especially dark states, or perhaps the low-lying Rydberg states around 7 to 8 electron volts. So that's work in progress. I will stop now. Thank you very much for your online attention, acknowledge support, financial support, and my colleagues in Debrecen, and you can find further details on that paper here.
Thank you, Benjamin. Thank you for your nice talk. I don't see any questions in the live Q&A box, so just a quick question. So if I correctly understood, with a full dimensional model, you can also consider non-adiabatic couplings with dark states, right? So you're, I mean, in the future, you can consider also dark states and not only bright states, as in this case.
Yeah, well, in a full dimensional model, yes, but then we would be able to consider those couplings to the dark states, which we did not, because we considered our simulations to be realistic only for very short times, just to see whether over 20 femtoseconds there is an effect of anharmonicity and such things, and how the electronic coherence suffers from that. Not much, but obviously there are many investigations that have been published for Vacher on the effect of non-adiabatic transitions, or the fact that states are non-adiabatically coupled. So that will kill coherence after, say, a few tens of femtoseconds. Obviously, that's very much depending on the system.
Yes.
Yeah. But then, yeah, that'd be the next thing to do here for pyrazine if it's a good toy model. Then.
Yes.
And we know that there is a strong non-adiabatic effect with lowest state, because that's been the focus of many quantum dynamics calculations. Yeah, sure.
Okay, thank you. I don't see any questions, but the audience can discuss with Benjamin later at the end of this session. So thanks again, Benjamin, and we can go on now with the next speaker, the last speaker of this session, who is Kalyani Chordia from Eli ALPS, Hungary. She's going to speak about decoding the response of correlated electrons to photoionization. So please, Kalyani, you can share your screen. Perfect. I cannot, yeah, okay, now I can see.
Okay. Thank you, Aurora, for the introduction. Hello, everyone who is attending the talk. I cannot see, I just see my screen. I'm Kalyani Chordia. I'm from ELI Alps. I'm doing my PhD under the supervision of Mashmika Hale. And today I will be talking about decoding the response of correlated electrons to photoionization. This work is being done in collaboration with a group from Heidelberg University under Professor Alexander Kulev. And today I will present some of our preliminary results on how the charge migration can be manipulated by using different tautomeric systems, using different conformers, or using methylation technique. So this whole study will have an impact on many, many fields. For example, radiation therapy, which is extremely complex process and has several factors involved. But if you consider a direct or an indirect effect of this radiation therapy, then we see it results in fragmentation of very basic building blocks of the biological system. Now, nature has a very beautiful way of even defending such damages. And so to have a photoprotective reaction, they undergo tautomerization. And so we can see that one single molecule can have different tautomeric system. It's not limited only to the biological system. But if you see a heteroorganic interface, which is very common now because of our flexible devices, the new Samsung phones or the LEDs, photovoltaics, or even sensors, we see that with this heteroorganic interface, we also see tautomerization. So if the tautomerization is happening, then is it true that it can affect the charge migration process? And if it affects the charge migration process, then we should be concerned because it can affect the overall efficiency of the device. Before I move forward to the talk, I will like to introduce what is charge migration. So charge migration is something you are disturbing the ground state electrons, and you are either removing one electron and sending it to one of the unoccupied molecular orbitals by photoexcitation, or you can completely remove it from the system by photoionization. Now, to this, the residual electrons are going to respond, and you have kind of disturbed their geometry and the ground state. So they are going to rearrange themselves to find a new, stable energy. So within few attoseconds or in femtosecond timescales, now in femtoseconds, I will say like safely around 10 femtoseconds, the electrons will move. And then once they find a position, they will tell the nuclei, okay, this is a good position and you can start moving and reorganizing. If they do not find something similar, then it will oscillate back and forth within a complete bond or within some part of the molecule. And this will result in the fragmentation channel because the nucleus don't know where to stop. So this will break the molecule. This is the outline of my talk, where I will begin with giving the motivation related to the studies which will help in molecular engineering, and some of the experimental techniques, which Alicia Palacio have already introduced us with the FEL, but I will talk about the other techniques. Then in the results, because we are triggering these dynamics with photoionization, I will start with comparing the ionization spectra of the molecules. Then we will see the charge migration in two separate states. Like first will be the sudden ionization response of the molecules. So how long does the electrons need to realize that a hole has been created? And then after that, once they realize how they migrate along the molecular skeleton. So in from 100 attoseconds to 10 femtoseconds, how the charge will migrate. And from this, we will compare the prototype systems and the tautomers, conformers, methylated groups. And with this, I will summarize my talk and give a conclusion and an outlook for this study. Which are the prototype molecules we have used for this work? So we have selected 3 molecules, uracil, thymine, and cytosine. These 3 molecules are very important for our biological system because they are one of the elements, building blocks elements for our DNA and RNA. Uracil is present only in RNA, thymine only in DNA, and cytosine is present in both. What is this chemistry-related thing, tautomers or methylation that I'm talking about? So when I move one of the hydrogen from the system to another atom in the system, then I'm doing tautomerization. So tautomerization is just moving one hydrogen to different atomic sites wherever you can fit it. So in uracil, I can move from one place to another. If it goes to the oxygen group, then it will form a OH bond, and this is called a enol because we have a C double bond O and a OH bond here, so it will be an enol. And what is methylation is the difference between uracil and thymine is this hydrogen here is replaced with a CH3 group, which is the methyl group. So this is methylated. The uracil is methylated. After methylation gives thymine. And in cytosine, if we move the hydrogen from this nitrogen on O, then it will give again the enolic form. But if I move it from this NH2, then it will give a iminic form. So these are the systems that I will talk about today. And the last thing is the conformers. So if the OH is facing towards this NH2, then it is kind of a cis conformer. And if it is facing away, as in this case, then it is called a trans conformer. Again, the group of Professor Alexander Kulov, they have studied an alkyne chain and carbon alkyne chain, where they showed that if they increase the number of carbons in the alkyne chain, then the charge migration behavior doesn't change, but the the duration for the charge migration goes on increasing monotonously. Further, in one of their other studies, they showed polyaromatic hydrocarbons where they increased the number of benzene rings, and they showed that there is a transfer of energy from the electronic degrees of freedom to the nuclear degrees of freedom. So it has already started how we can do this. And so if we are able to manipulate the charge migration in a system, then this basic engineering of the molecule will have a huge impact in several different fields. And it will be indeed a very interesting study and very important study. As Alicia Palacio has discussed already about the XFEL, how they can even study the correlation effect and how they can even make movies with this kind of study. There were, during late 90s, Weinkauf, he gave an insight on how the charge migration can be preceding the nuclear dynamics. And since then, this has been very much in use to use the fragmentation channel to trace the charge migration dynamics. However, this happens in femtosecond or picosecond timescale, where the initial response of the electrons can change a lot in that time. We have there is a work presented by Francesca Cagliari on phenylalanine, where they have used a charge oscillation along XH bond, and this also can show the fragmentation channel. And whereas Peter Kaus et al., he have presented his work on how they can control the charge migration using lasers. If somebody is interested in performing charge migration with, manipulating the core hole dynamics. Then there was a work there is work by Morov et al. On using attosecond transient absorption spectroscopy. And this is a new recent work where they have used excited state dynamics to reconstruct the charge migration. Okay, so in this work, we have used ADC theory. I will briefly go through this. So what is ADC or non-Dyson ADC? It's a single particle Green's function. Now in this one, how it is different from the Dyson part is you decouple the Green's function ionic part and the electron affinity part, and you propagate only one. So use only one part of it. So in the study, we use the ionization part of it. This is the spectral representation of the ionization spectra, where the K plus C and the F, which is the K plus C, will consider all the intermediate states, which will effectively give us the correlation effect. And this will run over all the excitation states of 1 hole, 2 hole, 1p, 3 hole, 2p, and over all the ionization energies. And the effective transition momentum here will give us the intensities of the cationic states. So the K plus C part will give us basically the cationic states, and the effective transition momentum will help us giving the intensities of these cationic states. What we understand from the ionization spectra is the solid lines is basically the 1 hole configurations. And the 2 colors in 1 line, it shows 2 hole 1p configuration. So if I ionize one of these orbitals, then I can see that the charge, depending on the positions of the cationic state and the difference between the position of the cationic state, the charge can oscillate with that time scale. And okay, let's remove 1 electron and see how we can propagate this. So once we have created the hole density, we need to propagate it with respect to time, for which we need a density operator. Now the density operator matrix will have a complete representation again of the intermediate states. And this will help us in understanding the correlation effect. So for example, here, in this diagram, we see that there is an intersection at 0.7 femtoseconds, 0.9, 2.8, 3, and so on. So at this intersection, what happens if there was no correlation effect taken into consideration, then it would just go, the home minus 9 will just move like this instead of going like this. At the intersection, the orbital actually interchanges its nature. So HOMO minus 9 will interchange its nature with HOMO minus 5, and HOMO minus 9 again interchanges its nature with HOMO minus 4. And this is how the correlation effect is taken into consideration. And these will show where the electron is excited to. Okay, so let's compare the ionization spectra for the molecules we have selected. I will start with using the methylation. Again, I will brush through what is methylation. So methylation is adding 1 CH3 group on the hydrogen, replacing the hydrogen in the system. So this is uracil. And after I replace this hydrogen with CH3, I get thymine. And if I check the ionization spectra of uracil keto and thymine keto, then I see that there is a red shift in the ionization spectra of thymine. Okay, let's check keto and enol, where I move 1 hydrogen to the oxygen. And I again see there is a red shift in the ionization spectra. And if I see this region around 15 eV, then I see that in thymine and in enolic forms, we see a lot of these cationic states with 2 hole 1p configuration. And as you can see, these 2 bars, if I remove 1 electron, it will oscillate really, really fast. So this will have a very small oscillation period. Okay, so when briefly, what happens if I have a methylated uracil and thymine, uracil, then the ionization spectra is redshifted, and after tautomerization, it is even more, is also redshifted. Let's check if it is true for cytosine, because we have tautomers there too. So the answer is no. In cytosine, we see a different effect. In cytosine, if we check keto and enol, then we find the spectra is blue shifted instead of red shifted. And what about the conformers is in the trans and the cis conformer, we see that the distance between the cationic states is increased when you have trans conformers with respect to the keto. But in cis, it is not that clear or profound that it is decreased or increased. So somewhere you will see a decrease, somewhere you see an increase. Okay, so let's check if we can remove one of the electron and initiate the charge migration process. I will show you a movie on the time steps from 0 to 50 attoseconds. And in this time, I would really like you to see how the electrons, they appear, the hole density decreases, and within 30 attoseconds, they will start migrating. And to briefly say what is sudden ionization is you have removed one of the electron and the molecule, so there is a certain time the molecule will take to respond, and there will be a certain time to remove the electron. So in sudden ionization process, it is considered that the time to remove the electron is shorter than the time the molecule takes to respond to this ionization. Okay. So this is the movie. So the electron starts appearing and now it starts migrating. So this is the sudden ionization response. So we can safely say in this, this particular movie, the sudden ionization response time is about 30 attoseconds, and it already starts migrating after 30 or 35 attoseconds. So the real question is it the response time is the same for all the molecular orbitals and for the systems? Then again, the answer is no. Here we see that we have considered 5 different molecular orbitals, both for keto and enol of uracil. And we see that in this picture, the response time increases as you go down in the orbitals. But in both these plots, we see 2 curves which are overlapping or moving in the same trend with each other. So what's the reason behind these 2 curves? These 2 curves have same molecular orbital symmetry, and the symmetry of this molecular orbital is symmetric. And so their response time is shorter in comparison to the others. Whereas the remaining 3 orbitals are correlated with each other, and as you go down, the response time is increasing, but the hole density that it is occupying is also increasing with this time step. What about the time after this response? So will it just keep moving with the same, dramatic behavior, or will it have a different approach? Sorry. Okay, so let's see. This is from 0 to say 1 femtoseconds. And I would like you to concentrate how in the beginning of the movie, it will move really very dramatically, but swiftly. And after that, it will start occupying some spaces and it will just oscillate between them. So this is the time where the nuclei will kind of rearrange themselves. They don't have to break the molecule if necessary. Okay, so they are moving, but now they are kind of understood how to do it, and so it will be not so fast. Okay, so now just oscillating between the places. So if we want to check how this particular dynamics can be manipulated, then we have to check how the uracil and the other molecules tautomers will change the charge migration dynamics. So first we consider uracil and thymine for the effect of methylation. And what we see is that in uracil and thymine, the place where there is a CH3 group in thymine is different, and this particular nitrogen is different, but the rest of the group, apart from the small change in the density of the hole and electrons, they have a same nature. If I want to check between keto and the enol form, what will be the difference is we see in the enol form, the charge density is more delocalized in comparison to the keto form. And this already suggests that the delocalization of charge will be higher in case of enolic form than in comparison with the keto form. Let's check for cytosine, as there are more systems there. So again, in keto and enol conformers, tautomers, we see that the charge is more delocalized in enol in comparison to the keto form. And if I check between the cis and the trans conformers of cytosine enolic form, then I don't see much of a difference apart from this small change. And okay, so maybe this doesn't have too much effect, because if we check the distance between the NH2 and the OH is quite large, and maybe this effect is kind of reduced because of the distance. But what about the iminic form, where the distance between these two is very, very short? So will it affect the charge migration? It indeed affects the charge migration. And if you check the cis form, then this particular region and this region doesn't have much of the charge occupied here. This shows that the cis conformer in this particular case is restricting the charge to flow in this region. So if you have this cis and trans kind of conformers, then if you keep it closer to each other within one bond distance space, then you might be able to restrict the charge migration in that particular region. You might be able to avoid the charge migration in that region. And in the trans, it helps in delocalization of the charge on the whole molecule. If we do this particular thing with the experiment, now, as we have learned in this whole workshop, that for this, we need attosecond pulses. So they are very, very short. But if we consider the broadband of these pulses, then it will be very, very wide. So that means I won't be able to ionize one orbital, but I will be ionizing many, many orbitals. And so to take into consideration this, we do an averaging of the molecular orbital charge density. So what we do is we take 5 molecular orbitals from HOMO to HOMO -4, and we consider the symmetric and asymmetric orbitals separately, and we average them. And let's check what's the difference between the two. So the difference between the two, we see that in A double prime orbitals, we see the difference between them. But in case of A prime orbitals, we don't see much of a difference apart from slight decrease in the whole density, or there is very minor change here. In keto and enol, as you can see, we see a difference. So even after averaging, the charge migration will be different in these two molecules. This makes me come to the final, well, not final, but towards the final slides. So in this talk, I have presented you our results on how the charge migration is during the first, first 50 to 100 attosecond time scale. And then from there, how the charge migration dynamics is evolving. And in order to go for molecular engineering, you can you can manipulate the charge migration using the different tautomeric forms, using the different conformers, be aware of the conformers, and also based on the different methyl groups present in the molecule. Now, this is the take-home message where we, after the analysis, we see which can be useful for, again, people who want to do molecular engineering, is if you have an oxygen or a nitrogen or sulfur, these kind of groups on the outside of the conjugated ring, then you should avoid that if you want more delocalized. Now, it depends really how you want the molecule to be. You want it to be more delocalized or less delocalized based on the application. So if you want it more delocalized, then first you can avoid having them outside the ring or outside the conjugation. And if you have them, then kind of it's better if you use the enolic or the tautomeric form, like enolic or iminic form. In this case, methylation will certainly improve the delocalization. And please be aware when you check the conformers of these systems. With this, I would like you all to, I would like to thank you all for your attention. I would like to thank all the funding agencies like European Union, European Regional Development Funds, and Hungarian National Research Development Innovation Project for funding our projects. I would like to give my special thanks to Victor Moshmi and Alexander for giving me the opportunity to work on this project. And I would like to thank my co-authors and colleagues for the discussions during this work. And without the HPCs and the IT support, I don't think it will be so smooth. So I would like to thank Zolt Sabo and Tarek Attila from the IT team for their immense support. Thank you all for your attention.
Let me see. I don't see any questions at the moment. So just a curiosity. What would be the effect of the Dyson approach on the spectra and on the description of the charge migration?
Okay, so if you consider the Dyson, then you will have, you will remove one electron and also you will excite one electron. So you are adding one electron there. So you will have the effect from both the sides. And this, I think, will really change maybe the charge migration process. But I don't know if it's done. Maybe
in this case, you have a reduction of yes, I guess. What is the main difference between the two approaches from the computational point of view?
I think, yes, there will be maybe the electron density just appearing. Maybe from the initial state, you will also see some electron density, which will be occupied on the higher orbital, like the unoccupied orbital states where it will be added. So, but I'm not the expert on this one, but I think Alexander Kulov and Victor can be able to answer this in the discussion.
No problem at all. Let me see. No, there is the control room. Okay, I don't see any questions on the live Q&A, so the audience can speak and discuss with all the speakers now, basically at the end of this session. So thanks again to Kalyani and thanks to all the speakers. Let me remind you, yes, that the 3 breakout rooms will be available now. So we can close this session. Hello to everybody. Thank you for attending the meeting, and see you in the afternoon with the poster session.
Thank you.
Goodbye.
Goodbye.